Priya Rose, Assistant Professor at ISP, to formally chair the session and invite the speaker. Dr. Priya Rose, please.
Thank you, Dr. Praveen. It's a great pleasure for me to have our speaker of the day, Dr. Rajesh Nair from IIT Ropar here. Dr. Nair has earned his PhD degree from Indian Institute of Technology, Mumbai, and then he also did his postdoctoral research in the complex photonic systems from University of Twente, Netherlands. Then he worked as Dr. K.S. Krishnan Fellow in Bhabha Atomic Research Center, and later worked there itself as scientist D. Starting from November 2013, Dr. Nair has joined as an assistant professor in the Department of Physics at IIT Ropar. He has made notable contributions in the field of nano-optics, such as observation of sub-Bragg diffraction of waves in crystals, the first ever signature of three-dimensional photonic bandgap, etc. He has published several papers in high-impact journals, and many international journals has highlighted his works, like Nature, India, Science, Optics and Photonics News of Optical Society of America, etc. Dr. Nair was the recipient of Dr. K.S. National Academy of Science and recently he was awarded fellowship in 2020 instituted by the Government of India. His current work focuses on studying the spectral and temporal modifications of spontaneous emission of solid-state defects using resonant photonic structures. With this very brief introduction, I heartily welcome Professor Rajesh Nair to deliver his talk. Over to you, sir. Thank you.
Okay, is I audible?
Yes, sir. Please go on.
Okay. First of all, thank you for this invitation and introductions. And this is the first time I'm giving a talk at ISP. Even though from a distance, I watched the growth of ISP, and congratulations for your Silver Jubilee. And if this also, when I got these invitations, my memories put back around 16, 17 years back, where I've got a first ever chance to attend a conference, a scientific conference, which organized by ISP. Maybe Professor Pramod knows in 2004, the Photonics 2004 at Limeridian. Okay, so nice to be here, and I'll share some of our ongoing effort and or some of our understanding of how we can modulate the light transport and emission using certain photonic structures. And we go from ordered structures to a tailored disordered structures, okay? So I'm from IIT Ropar, which is extremely north compared to Cochin. Okay, so it's in Punjab, but it's very close to Chandigarh. So it's a new institute of 10-year-old. We have a MSc program, PhD program, and we'll be starting a BTech program in physics in next year, 2022. Okay, so here, so you probably everybody appreciate these beautiful colorations in nature, and at some point of your life you must have noticed these colorations. And this is one of the best examples of a photonic structure available in nature. And if you really look at the structural features of these peacock feathers, and you can see that very nice subwavelent nanostructures inscribed on it. And if you measure these properties in the laboratory, these structures actually show resonances. And the right side plot is something which we measured in our lab. So I'm going to talk about in this probably 45 minutes or so, this kind of structure, what we can use it, and what are the more fundamental physics we can learn, and with some possible applications. So I will be focusing on more into fundamental science. So our research group at IIT Ropar started in 2014. So primarily we work on a field called photonic crystals, which I will be talking today also. And then we also do a research in the area of disordered photonic systems, where the light gets completely scrambled inside the medium. And off late in 2016 onwards, I got interested towards the quantum photonics. And so we work on primarily a system called nitrogen vacancy centers or color centers in diamond, which is an ideal system to generate single photons in the lab. So, and we are also recently started working in photonic cavities and metasurfaces, so which probably will discuss in some other time. And I'll be covering these areas. I'll give you some important results which we have achieved and our understanding or our viewpoints on these results. So the plan of my talk, I try to give a very broad introduction so that I'm sure mostly the students are attending. So they try to understand what we are going to talk. And then we'll go to the state of the art research, what samples we make, and how we're going to understand that. And lastly, I'll also touch upon our effort on quantum photonics, and then I'll conclude my talk. So as a historical background, the light propagation in any nanostructures or photonic structures, it's actually traced back to 1887. It was the first paper by on this kind of structures by Lord Rayleigh, and he considered a laminated medium, basically a periodic structures where the mechanical functions are periodic. So he trying to understand how certain thin plates shows colors, and he trying to understand, trying to explain or trying to bring out the physics of these color formations. Okay, now these are very standards in books, but look at the year, it's 1887. So he considered a system like this. You have an alternating refractive index or alternating mechanical properties. And if you send a wave or wavelength of the train of the progressive wave, if is equal to the double the interval, basically this interval is this the d here, this total thickness, and basically it means lambda equal to 2d, which we know as a Bragg condition now. Okay, so even in 1887, the Lord Rayleigh has put this in the community that there is a possibility to have a laminated structure, and if you can do that, probably light reflection, the coloration in many systems can be understood. And you can see the spelling differences in the all. These are all text I copied from his this paper. Okay, so in the you can see the reflections that time. It's very different from nowadays we write the reflections. Okay, so it is known in 1887, even before Bragg came up with his famous Bragg diffraction formula. Then it was quite silent. Then 1934, 35 times from our own country, Professor Sir C.V. Raman has quite interested in why does colors occur in nature, and he categorized colors into two types. One is called iridescent type, another is non-iridescent type. Iridescent means when you change the angle, you see different colors like a CD. But if you look at your color of your dress, it does not change. So those are non-iridescent colors, so basically due to the absorption of pigments. So he was interested in why certain birds, certain natural creatures show different colors when viewed at different angles, or the same color at any angles. And in 35, another paper he wrote in Proceedings of International in Academy of Science, where he has tried to see that why some seashells show different colors. And he also used, this is again his own sentences, which owe their origin primarily to the laminated structure of this structure. So again, he's talked about laminated structures, and probably nobody knows this work in the West, or nobody cite also in this work. And if you go through this complete work, it's so brilliant guy. So he has nicely written and mathematically proven that these things are possible if you are able to make this kind of structure, the natural coloration. Then the optics moved to the advent of lasers, then fiber optics and nonlinear optics. Then in say soon after the discovery of laser in 60s, there was a need to control spontaneous emission, because probably if you have done the laser science course, the the spontaneous emission is considered as a loss in the system. So one has to try to avoid the spontaneous emission. So people started working on looking different aspect. Is there a way we can control spontaneous emission? Because fundamentally, quantum mechanically, you cannot control spontaneous emissions. But is there a way? So one paper which came in 2070s by Russia, by the BICO. So he said that spontaneous emission of an excited atom is located in a periodic structure. So it's again laminated structure, okay, the same meaning. And then at a paper at 81 from MIT, Danny Klepner, the title itself is saying inhibited spontaneous emissions. So people trying to see whether is there a fundamental way to control the spontaneous emissions, and people are proposing different approaches to do this controlling the emission of light sources. Then in 1987, there is a huge change happens when Yablonovich put up in a very simple thought experiment. Okay, if you read this paper, physical related single author paper, you don't see any mathematics, you don't see any much graphs. It's like a reading a short story. Okay, so it is his thought experiment. Can we control spontaneous emission? And he said, if we can have a three-dimensional periodic structures, basically you have a three-dimensional laminated structures, which is something called a band gap, basically a band gap for light, the spontaneous emission can be rigorously forbidden. And none of the previous work got any much citations, but the Ablonovich paper got the highest cited paper in the history of PRL, which I think more than 20,000 now. The reason why the work was so much momentum because it's put up in a technological perspective to achieve what is called low threshold lasers. And in the same issue, maybe a coincidence, Professor Sajeev John, he actually born and brought up in Kerala and went to US with his parents at the age of 5, I think. So he come up with a paper that if you have this kind of laminated structure, if you can introduce some disorder into that, okay, I'll tell you detail what is this all means. You can have another interesting property which is called a localization of light, similar to electron localization, Anderson localization. So these two papers in 90s has actually put the field of nanophotonics into a perspective, then people trying to jump and do theory to try to make these kind of structures, whether it's really possible, because if it is possible, it is actually challenging the fundamental physics. So now we move to technical slides. What does all this means? What is laminated structures and why it is so? So basically, I'm talking about a laminated or a stratified or a periodic medium. I use these words quite repeatedly. So all means same. So basically, I take a dielectric with a dielectric constant epsilon1 or epsilon2. And if you take a piece of dielectric, you must have studied in a Griffith electrodynamics that if you solve Maxwell's equation, you get a wave equation for light. And if you draw the wave equation solution as a frequency as a function of wave vector, you get a straight line, which is a dispersion relation or light line you call. It's a straight line relation because omega equal to c by n into k. So it's a straight line. The slope will give the velocity. So if you, instead of having a single layer, now you imagine I have a two different material, which is as a dielectric constant epsilon1 and epsilon2, and I periodically arrange in one directions with a periodicity d. So this is epsilon1, epsilon2. Again, I repeat epsilon1, epsilon2. And epsilon1 is greater than epsilon t. And here A is equal to D only. Sorry for this typo. So the dielectric constant is periodic in one direction. And if you try to solve Maxwell's equations, it is not an easy task. It is really tedious job. And if you are so much good in maths and have a patience, one can do in one dimension at least, where you make epsilon is a function of space. In the book, you see epsilon is kept as a constant, but here epsilon is a function of space in one direction. That's why I use it x. And if you solve it, the result will be quite astonishing. The frequency versus wave vector is showing a break in the dispersion relations. So if you look at this yellow region here, at some frequency range, there is no propagation constants, and the dispersion relation show discontinuity. So what happened is at this frequency? Suppose if you send light into the structure at these frequencies, for example, I have the structure, I launching light at this frequency, which is within this yellow region, the light get Bragg diffracted back. Okay, the light cannot propagate. That means there is no allowed wave vector in the system where the light can couple. In fact, the whole this light actually return back, interfere constructively according to the Bragg conditions. And if you look at the field in this system at these frequencies, this is some calculation I did. So if you look at take a frequency in this yellow region and send look at how the field intensity in the structure, you can see that the field intensity actually decay into the structure exponentially. And this length of attenuation we call as a Bragg length in the system. Okay, so it's not such in something rocket science. What you did in condensed matter, we have a periodic atoms, we have a X-ray diffractions. You're similar to, you're going for an optical diffractions, where diffraction which you can see with your eyes. Okay, so to achieve that, we need to have a periodic medium, and a similar condition like Bragg condition for condensed matter physics with slight modification is also applicable here. Okay, and this is the very essence of all these photonic structures using controlling the spontaneous emission or other applications. And this frequency range, which I call is a yellow region here, which is called the frequency gap or a stop gap. That means this frequency within this yellow band cannot propagate into the structure. If you have this structure, the light will be reflected back to you. Okay, and if you are looking from the backside of the sample, the light does not reach you. It does not mean that the light is absorbed, but rather the light is just reflected back to the incident medium. And people mistakenly call this is photonic band gap, but I want to make a clear inferences here. This is not photonic band gap. This is a direction dependent frequency gap. So sometimes we call it stop gap. Now imagine the similar thing, the thing I said in one dimensions, can we think in terms of two direction or three directions? And the most interesting will be a three-dimensional system. So you take a material, you have a silicon wafer or a glass or something, you drill periodic holes. You have a drilling machine, you can make holes in it. The diameter of the holes is, let's say 300 nanometer in diameter. So that's where the challenge comes in terms of fabrications. And you can see that, so there's a periodic structure. I'm sending light from outside, from different directions. The light comes from here, it gets reflected back because it cannot propagate because of the frequency gap in this direction. And I send light from the bottom, it cannot propagate. So I send light from all directions of the crystals, all direct in the 3D, because it has a 3D laminated structure, the light cannot propagate in the medium. So now the question that naturally asks, what is great about it, right? I know from condensed matter where you have atoms are in the Armstrong periodicity, where I'm going to sub-wavelength micron scale periodicity. It's just a scaling of the gaps. Things got interesting and things got this much effort the people are working is because if you keep a light source inside, imagine I have given you this sample and I'm putting a light source. When I say light source, it's not the light bulb in your room, but rather a quantum dots, a dyes, or anything which emit light, which can put it in these nanostructures and give some energy, let it excite, and the emission will happen. And let's see the light get emitted. Now the emitted light, as it tried to propagate, because these are spontaneous emission, this will be in all 4 pi steradians. And so the light will try to leak from here, but it cannot go because of the periodicity. The light get internally back reflected, and this light also get reflected back. Because of one condition, I make sure that my emission wavelength is matched with the frequency gap wavelength. That's why I use the both orange color here. So the emitted light cannot come outside. And if you look at the density of states for these kind of system, if you calculate a photon density of state, basically the number of states available for a given frequency range, an emitter can make a transitions. And if you look at the density of photon state as a function of frequency, at this frequency gap, the density of states goes to 0. That means, in reality, the density of state is reduced. Had been if you don't have this periodic structure, you have a homogeneous medium where everything look like blue color, is a single dielectric medium, the density of state goes as a function of frequency square, omega square. And now I have a system where the density of state, a photon density of state I can engineer. And these are man-made systems, so I can make it in any frequency, in any direction I want. Now, what is the advantage if I have a density of state is 0? Now, if you go back to your books, you go back to your advanced quantum mechanics, basically time-dependent propagation theory, you have a two-level system. This is something which we easy to discuss in class, which has not much meaning in reality. So if you have a two-level system, so you have a ground state, you give some energy, it go to excited state, and the decay rate of this, hello? Okay, the decay rate of this emission is proportional to a constant, which is a dipole moment, which is fixed with the moment you choose an emitter, and a function called rho as a function of frequency and space. There should be a space function also here. And this rho is called the density of photon states. Right? So if you go to a Griffith quantum mechanics book on the, I think in the second last chapter, he has done an elaborative derivation on how we can arrive these equations. Okay, 3 to 3 page mathematics you have to do. We can show this equation finally comes. So this says the decay rate of an emitter once it is excited is depends on a quantity which is called the rho, which is the photon density of states. Now, if you have a system which can change this rho in frequency and space, then you can change the decay rate of an emitter. And that's what these kind of nanostructures does, or photonic structure does. Because now I have a system where at certain range I have a density of state 0. The density of state is 0 means gamma rate 0. So the gamma is 0, that is the decay rate is 0. That means the lifetime, which is inverse of rate, is infinite. So I have a system where I cannot even spontaneously light cannot emit, at least in ideal theoretical situations. But in reality, there are a lot of dephasing mechanisms, so the light will leak out. But now this is the reason why the photonic structures or a photonic band, these are called photonic crystals, photonic band gap materials, is got a lot of interest and excitement and applications. Okay, just because this is a system which can use to control the emission, not because of Bragg diffraction optical on the optical wavelength, but in a sense it is the this internal diffraction that will happen. So I'll show you in my talk how we make the samples and how we do experiments to show you. I'll show you how intensity or the rate is been altered in the experiments. So soon after the 90s discovery, all the people jumped, okay, let's make the samples. And that is where the difficulty arises. Because in condensed matter, the crystals are given like God was given just a nice periodic arrangement of atoms. But here we are talking about making a periodic structure of dielectric constants at the sub-micron scale in all the 3 dimensions. And one of the things we need when you take this laminated structure, I talked with the 2 refractive index or 2 dielectrics. So one of the things we need is it should be high refractive index. And the nature does not allow it to have arbitrary refractive index. The maximum you can have is 3.5 at 1.5 micron wavelength. And the material should not absorb light. That is another difficulty in finding materials. And the most important, this is the fabrication challenge, perfect ordering. Even a small variation, small discrepancy in the ordering will kill all the optical features of the system. It looks nice in some pictures, but it never give you any optical response when you do experiments in the lab. So keep in this mind, people try to make many ways to make the sample. One way to look at the fabrication, semiconductor fabrication, where you have a electron lithography and reactive ion etching. Then you try to make these kind of structures. Basically, you take a silicon wafer or so, you make angle etching. You can see that there is a variation refractive index. So this region between these circles are air and the other medium is air. So you naturally get a variation refractive index between the air and the silicon. And this is another system which has been one of the champion structure which give these photonic band gap features, where you can again see that you take a piece of silicon, you etch first from the top direction and second from the cross section directions. So you get a kind of a network structure, but these are nice periodic structures. And the third structure, which is quite popular, probably 70% of the community use this structure because it's easy to make and it's not that expensive, called self-assembled system. And we also going to talk about these kind of structures quite a lot in this talk. And this is the way in the laboratory sample look like after your growth. Okay, if you're lucky and if you are good in growing the samples, one can grow the sample with a 1 week time, and you can see nice diffraction. The color you see is that when you shine a white light, the light is reflected back to you because of diffraction. So because that light is not allowed to propagate into the system. This is what exactly happens in a peacock feather. When the sunlight hit on that, the different colors are reflected according to the periodicity of different barbels in the peacock feathers. And I'll show you one of the measurements we did in our lab to confirm this kind of resonance from natural systems also. So in our lab at IIT Ropar, we made these samples. So we buy these microspheres. These are 280 nanometer, 300 nanometer in diameter, 0.3 micron. So we buy this, we have some understanding, we have some idea how to make it. And our recipe works actually from 200 nanometer to 1.6 micron. So we can make these samples. So this is one of these image of the sample, which is a scanning electron microscope. And I intentionally show this picture rather than showing a very nice SEM picture, because you see there is a cracks, there's a gap, and there is a missing sphere here. There are dislocations here, and there may be one layer is missing from here. So these kind of things happens in real samples. And one has to avoid all these things. And that is why making samples and that is another reason why is this nanophotonics, even theoretically it advanced a lot, even at the single quantum limit, but experimentally the field is still in very challenging because of the fabrication of the samples. And when you say fabrication, not by SEM picture, but by the optical response these samples should give. So this is one of the picture we have, and then we grow the samples. And how do you know that my samples has a frequency gap or not? So typical experiment, what everybody does, you measure the reflectivity of the light as a function of wavelength. Okay, so I measure the reflectivity, the y-axis, as a function of the wavelength of the light which is incident on the sample. So you see there is a peak in reflection at some wavelength, which is called 600 nanometer. And on parallelly, I also measure transmission of light to the sample. Okay, and if you look at the transmission, it started with the high transmission at a high wavelength, and as I decrease the wavelength, the transmission reduces, and it reach a minimum value where I get the maximum value in the reflections. So you have a system, you have a piece of glass or sample with you. You send all these light of this wavelength, and certain frequency or certain wavelength centered around 600 nanometer cannot propagate. And the light which is absent in transmission, it's not absorbed, it's completely reflected back. And now you see that if I add the long wavelength, which is at the 750, both transmission and reflection, it is not up to 200. That means there's a huge scattering in the samples, and that scattering happens because of these kind of defects, disorder, everything put at one umbrella. And this was one of the challenges and in the field of experimental nanophotonics, how to avoid these defects. And later I'll show you when defects is also a good thing to have, because it is a defect which make people also interested. Okay, so we estimate all these nice parameters, and it's all agree with theory. So we are very happy with that, and we wrote many papers, couple of even in fact 3 papers in physical review on the optical properties of this. Okay, but these samples have a problem. If you look at a bit of helicopter view of the sample, this is the way it look like a cricket pitch. So you have a grain boundaries, and this is from the scale bar you see, it's 100 nanometer. This is the region I picked from here. Okay, but in real, this kind of measurement is not possible from this. In the lab, when you measure your very large area sample, so you can, these samples are divided by these kind of bits and pieces. So you can see the scale is 100 micron. So people convinced around 2010 to 2015 times that these self-assembled systems are not good for many optical experiments because it has huge number of disorders. But we thought maybe clever experiment can avoid this. What about measuring from this small region? Instead of doing measurement from this whole region of the sample, let's focus on a small region here, probably a 10 micrometer area. 10 micrometer square area. So that's what we are going to do, and that need a lot of sophisticated instrumentation development, because no commercial system will give you no spectrometer you can measure light from a 10 micrometer region. You need to have your own setups, because in a commercial spectrometer, whatever you use, the beam size is 5 millimeters. So 5 millimeter means it may be much larger than this image itself. So when you do a conventional measurement like the spectra shown here, you may be mapping thousands of these kind of bits and pieces. So all kind of ugliness in your samples will come back to your measurements. So we thought of doing an instrumentation or develop these facilities where we can measure from this small region. So we started with the DST project on this in 2015. And this was the first setup we developed at our lab in IT Ropar, so which we call it a micro reflectivity setup. So basically, I have a white light source, basically a Fianium superconducting laser. So I expand the beam using telescope and all. We send to a sample is mounted here using a particular objective called reflective objective. It's like a lens, okay? So usual objectives are made of glass, but this is made of metal mirror reflection, okay? And you collect the light, and this light is sent to a fiber, which is connected to a spectrometer. Since I'm talking about nanostructures, I'm trying to measure from 10 micrometer kind of sizes. I need to know exactly where I'm measuring, right? Because I cannot, otherwise I have no surety whether I'm measuring from a bad region or a good region. So we also build a in situ camera with this. So there's a camera here which give me live image during measurement. So this is a kind of a picture. You can see that the sample picture in our camera using this setup, and the white light laser is spotted here. So I can, and this sample is kept it in a scanner. So I can move the sample anywhere, so that I can move to this region, I can move to this region, or I can move to a bad region and measure it. So with this setup, we are able to achieve very accurate or very precise measurement from a region which is almost free from the defects. Okay, not 100%, but probably 98%. And this was a remarkable setup in the sense we can not only use for these structures, we can, if you have any sample of few microns in size, nanowire, 2D materials, and we can easily map the reflectivity. And you can also see in with you in the live image where does the measurement is actually happening. So, and I said I use this particular objective, the reflective objective, not the glass objective. The reason is that when we do a wide light spectroscopy, we need to avoid the chromatic aberration as much as possible. The glass objective, you can get a plan chromatic, chromatic objective from companies, but that is chromatic only for few wavelengths, but we need in a broad wavelength. So that's why we use instead glass objective, a specially made objective from Edmund Optics, called a reflective objective. Okay, nowadays it's more commercially available, and that time it was quite rare to get this one. So we could avoid this chromatic aberration. Otherwise, your result may be wrong. Okay, so this itself as an instrumentation paper we published in RSI in 2019. Okay, now I have this sample. I have this kind of grain boundaries. I mounted this sample. I measured the reflectivity as a function of wavelength in our own setup. Okay, the setup we just shown in the last slide. You can see that the reflectivity goes up to 100%. And it's a very nice reflectivity. And if you do the same sample in a commercial spectrophotometer, and you can see that because a large beam size, the result is much reduced, just like a 40–50%. And in the long wavelength, if you look at this, I zoomed here, you can see these nice fringes when we measure from our setup, which is not that clear in the conventional setups. And these fringes, which is basically a thin film interference fringes, which help us to estimate the thickness of the region you are measuring. So without any extra measurement like a profilometer or anything, I can measure the thickness just by measuring the optical signal. So this was a very nice setup. So we could measure from n number of domains as we wish. So with this setup, we realized that, okay, if you measure from small region of the sample, we can easily get very nice reflectivity or the frequency gap. And with that, we wanted to also look at whether the peak of feather can be imaged in our setup. So if you take a one single barbel of the peak of feather, you can see that this is a live measurement picture we took from our lab. So you can see the laser is focused here, and I took different type of peak of feather. We can see that it shows different resonances, different reflectivity bands. So when you put all these things overlaid each other, you see a very nice colorations. That's what you see in those systems. We started with a fun at that time, but now it became a very serious activity in our group. A couple of students are working on this kind of biophotonic structures, or biogenic photonic samples. Okay, so then we wanted to see the, okay, we are happy with that. We got the nice frequency gap. Can we do emission measurement with the samples? Okay, so what we did, we embedded, we made the samples with the dye incorporated spheres. Okay, so the dye is the emitter. So we made a setup again to measure the PL spectra, again from a small region of the sample, just like the reflectivity. Again, I have a camera so that I know from where exactly I'm measuring the sample. And we map the intensity, the PL intensity as a function of wavelength. And the black one is the reference sample, the typical dye emission centered around 600 nanometer. And if I measure from a larger region of the sample, I get what this red curve. So there's a bit of changes in emission intensity. And if I do a single domain, when I say single domain means I mean this small region where there's no defect as much, I could see a huge change in the emission intensity. So this is the way the spontaneous emission intensity is changed. The intensity is, in fact, is suppressed at the frequency gap. Okay, we made the sample in such a way that the frequency gap coincides here. And if I take the ratio between the black, the blue divided by black, or the red divided by black, and this is what the community, the way we represent data in this field. So we can see that there is a intensity suppression. It's around 60% we got from a single domain. And this is precise measurement, which actually help us in doing these nice measurements. Otherwise, people believe these samples are not that good for this kind of experiment, largely because of the inherent disorders. And second is the very less index contrast of the sample, because these samples are made of polystyrene or polymethyl methacrylate spheres, which has a very less index. So the contrast you get is usually around 0.6 or 0.59, but ideally you look for system like 2 refractive index difference, which is not the case for us, because then we need a really electron lithography fabricated on silicon or gallium arsenide. So we were quite interested that yes, we could at least see a very huge change in emission intensity. So probably this will be a nice to proceed further. So then what we did is we painstakingly take a lot of these regions. Okay, so we measure intensity spectra or the intensity separation from each of these domain, and you can see that there's a huge variation suppression across the sample. So when you see a result in literature, somebody show once intensity spectra. Now the question is how much reproducible? Is it the same everywhere in your sample? So you can see that there's a huge variation across the domain. And if you look a little bit within the domain also, you can see that it is narrowed quite a lot actually. And that distribution is reduced when you measure within this one single domain. And this suppression in emission, it is not arbitrary. It actually scale with this parameter called the L by LB. Small l is the thickness of your single domain, which we measure from reflectivity spectra of the same domain, and LB, which is a Bragg length, which we also got from the reflected spectrum. And it's not arbitrary scaling, it's a linear scaling. So if I have a suppression, if I plot suppression as a function of thickness of the sample, you take it as a thickness, a normalized thickness. And if I increase the thickness of the sample, the suppression is quite increased linearly. And this is repeated for another sample and which is reproducible. And that way back, there was a report in optic letters that if you have a samples of different thickness, the emission suppression, this is in the intensity. If you have 3 layer, this much intensity suppression. If you have 5 layer, you have intensity suppression. So the intensity suppression actually increases with the thickness of the system. So that's what we scaled up here. And you can see that the paper was in 2002. So the wavelength they're talking about 10, 15 micron, because nobody thought maybe at that time, probably this can be done at 0.5 micron, 0.6 microns. So this was a very nice result we got, and we sent it to optic letters to get it fast published. And there was sent it to 4 referees. 3 referees said yes without much change, but 1 referee said no. And people in this business knows the democracy never work in peer review systems. So editor reject the paper. And we know the reason why it was rejected. We know even before submission that there is a problem with this result. When we claim that the spontaneous emission is has a finite size scaling or a size dependent scaling in the system. The reason is, if you want to talk about any change in spontaneous emission, intensity is just a signature only. One cannot quantify just with the change in emission intensity that my emission is controlled or changed. Because if you have a light in your lab or room, you put a glass plate, the intensity is reduced. That does not mean that the emission which happened from the emitter is altered. That is because of filtering effect. So the reason what the referee concern, or which we even aware of it, that the decay rate is not is proportional to density of states. So if you want to say spontaneous emission is scalable, we have to do actually a lifetime measurements, and to show instead of suppression intensity, the lifetime should scale with that. So we did that measurements. And before I go to that, what is the L dose? Probably if somebody is still not clear. So when you have an excited atom, when you put an atom into excited state or electron, it has to decay back. So that depends on how much available states it's. For example, here you have a system where there's a large density of states, like a cavity system. You increase the density of states. Okay, there are multiple ways the photon can make a way out. And if you have a density state is reduced, that means there may be only one way the photon can work, or maybe no way a photon can make a transition in the ideal photonic band gap. So how we do this experiment, how you do measure the density of states? You have a sample, you excite it, you measure the fluorescence decay time. And if you're able to measure the decay time or the decay rate, you can relate that for a given dipole, the density of state related to the decay rate. This gamma, which you got from the experiments, and for a given sample, the dipole is fixed, so the density of state can be scaled. And it is nothing great in optics. Even if you look at nuclear physics and all, the decay happens in the hundreds of years or thousands of years. Whereas in optics, decay happens in the time of nanosecond or millisecond. Okay. So we need to do a decay rate measurement. We need to do a time resolve measurement to completely guarantee there is a scale, there is a emission changes. So we did another experiments. We had to, because again, we had to build up facilities, because commercial system doesn't help you here, because signal has to be collected from tens or 150 microns regions. So we build up a time correlated single photon counting using that method. We build up a decay rate measurement system. So again, we have a picosecond laser here. So this picosecond laser is green laser, which is excite the dyes and collect the emission. Again, send it to camera, because we want to know whether we are measuring from the right region. And this is a typical decay curve we get in the lab. And the residual is that once you fit the curve with the appropriate decay function, single exponential, double exponential, structural exponential, the choice is yours, which one you like and which one is the best you can explain your data, and which we follow a double exponential fit following this works in the physical letters, where it gives convincing lifetime for us. So we did these measurements. So this is a typical lifetime we measure from the gap. Okay, so here the intensity, the spontaneous emission intensity is plotted as a function of time. So the black one is a reference decay time of the dye suspension, which one you are using in the sample, which shows a typical lifetime of 1.9 nanoseconds. And if you measure from the stop gap region, basically at 600 nanometers, the blue symbols here, and fitted with the double exponential, the lifetime you got is around 3.9 nanoseconds. So lifetime is reduced. That means the decay rate is slowed down. Okay. Sorry, the lifetime is increased. That means the decay rate is reduced. That's why the decay becomes slower when you measure the band gap. And there is always a debate in the community. Is it this is the correct way of compare? This is the reference is correct. And there is another school of thought which says this reference is wrong. Rather, one should see a wavelength dependence. If the emitter is emitting at this wavelength, the decay rate is slower. And if an emitter is emitting at outside the gap, the decay rate should become fast. So we have been forced to do that measurement also. We did at 570, close to this band edge. And you can see that still there is a increase in lifetime for the emitter emitting at the band gap frequencies. So in a way, we can see that this is a clear indication that the spontaneous emission can be controlled and the lifetime is changed. That means I can control the density of states of the system. So similar to the intensity measurements, we measure again from many domains. You can see there is a huge fluctuation in the lifetimes because of the variable thickness of the sample. And if you go with a single domain, you can see that there is a clear distinction between the lifetime measured from the at the band gap and corresponding to the outside the band gap. So there's a clear increase in lifetime. And if you look at the lifetime as a function of normalized thickness, is indeed shows a scaling. And this was one of the great results. And when we are doing this experiment, there was a theoretical report in PRL where they show the density scales linearly with the system size. And here it's a theory paper, so they calculate density of states. Here we are doing experiments, so we measure the decay rate, so the lifetime, which is also scaling with the system size. So finally, it got accepted in in optic letters. And so we did a very elaborate measurements. Those who are specifically interested in more about it, we have written a follow-up detailed article in Physical Review about how we can understand the spontaneous emission systems. So at the band gap, it shows scaling, and outside the gap, it does not show any scaling. Okay, and this scaling is not arbitrary. It does depend on the normalized thickness of the sample. Okay, so maybe in another, maybe I've eaten up a lot of time. And so in another 10 minutes or so, I'll show you some very interesting activity we are doing. So till now, you must have heard that I was always telling disorder is the problem. Disorder is, we have to avoid disorder. But as I said, it is a disorder which makes anything interesting, whether it's a crystal, whether it's a human being, whether it's a society or anybody. So we talk about, we got interested to how to go from a perfect system to a disordered system. And I don't want to go arbitrarily. I want to go with some control. And control disorder is a dangerous word because you cannot control disorder, right? If I ask you to sit in a class in a regular, it's easy. But I ask you to sit in a irregular way, I can predict who will go and sit where, right? So but in the recent times, the kind of disorder we are talking is what's called a correlated disorder. That means there is a spatial correlation between the scatterers, or what we call it, so there is a short range order. It's not completely random, but there is a hidden short range systems. There was quite a lot of recent works. It's actually follow from the C.V. Raman work, which is shown in my third slide. You can see that this is some literature, I think is from PNA's paper, where they're interested in these kind of coloration comes because of short range order and these kind of bird feathers. And people try to simulate this using Monte Carlo simulations in the computer. You can see that you have this 30% is a disorder, 50% disorder increasing, and there's 30%. And then you look at the structure factor. Structure factor is a factor which will give you there is a resonance in scattering. Probably you must have done in a solid state physics. And there is a structure factor shows a peak. And this theoretically shown it even in fact affect the dose, the density of photon states. So we were quite excited by these systems, and we thought how to make this disordered sample. When I say controlled disordered sample or a correlated disordered sample. So before I get into my experiments, when you talk about disordered samples, um, when a light enter a disorder medium, when I say disorder, please understand, when I say disorder means is a disorder in dielectric constant. In the previous all the slides, the scatter has a definite positions and I can have a definite periodicity. But in a disorder medium, the systems are quite scrambled and random, so I don't have any spatial periodicity in the system. Okay, the white paper, milk, powders, you take a chalk powder in your class, these are all nice disordered system. Okay, and and if you have a increase the disorder, the thickness of the sample, the transmission drops down because light is getting multiply scattered. Okay, and the scattering length scales, instead of Bragg length in photonic crystal, we talk about scattering mean free path and transport mean free path. And if this transport mean free path is much less than the sample thickness, we say the light is diffusely propagate. Okay, so I'll use these numbers later in my slide. That's why I just put a one slide to understand, tell you these are called scattering. Because if you have a disorder medium, to characterize your disorder medium, you need to measure those numbers, what is scattering and the transport mean free path, and there's a way to measure it. Okay. So we made a sample following this paper in advanced materials. So it's easy because we have a lot of control on colloidal self-assembly. We thought of making these kind of correlated structures. So we made this sample. If you have to rigorously look at these things, you can see it's not completely random. There are short range order. And how do you ascertain there is a short range order? I do a pair correlation function. And this kind of nice oscillation up to 1.5 micron, which actually shows there is a ordering, a short range order. And if this sample does not have a short range order, if it is made up of a powders like a chalk powders in your lab, you do that, take a same picture, do the pair correlation, you don't see any oscillations. You see any decay. There is no correlation between the scatterers. That means there is a scatter here, there is another scatter here, there is another scatter here. And this goes in a periodicity, but only up to 1 micron. Had it been a photonic crystal where I have a long range order system, I could have got this oscillation without ending, with it never exponentially decay because it has a long range order. So this is one way to check it. And then what we did a measurement. We did a measurement, we passed the light. But when you characterize a disordered sample, it is not the linear transmission but matters. When I say linear transmission, you have the light which is coming directly to you. But in a disordered medium, the light gets scrambled, the light is randomized. So it propagates in all directions. So you send the light, it propagates in all random directions. So we need to collect what is called the total transmission of light, which not only account the straight path, which also account the other angle scattering also. So we have a small setup which is called integrating sphere. You keep your sample here, you pass your white light laser connected to a spectrometer, and you can measure. It's a very easy measurement. It's not a very difficult or anything. So even a master student can easily do it. Okay. So we measure total transmission as a function of wavelength, and this is a black curve is for a sample, TiO2 powder, the paint, the TiO2 powder or the chalk powder kind of thing. And you can see that as your wavelength decreases, the transmission decreases as expected for any disordered medium. But when we do for other sample, which is a correlated scatters or short range order samples, we see there is a dip in transmission spectrum. It's not a monotonous decrease like just like a powder. And this was initially we got quite worried because we thought we are doing something mistake. I'm talking of the year 2017-18, but later we understood that no, it is correcting because these resonance or these dip happening because of the short range order, and this has to happen because there is a local ordering present in that. And if you make the same sample using a long range ordered sample, just like the photonic crystal I talked, you can see that the gap is preserved much better way, because here background is not a big issue because there's not much disorder, but in this background is quite bad because there's a lot of multiple scattering happening. So at least for the we could show that yes, indeed these short range order samples can be made, and this does show a frequency gap similar to the long range ordered one. And this was the first ever demonstrations, even though there are huge theory paper right and left published in PRL on correlated scatters by many groups trying to achieve this kind of sample. Again, experimentally it was a really challenge. How do you make these samples? So this is not the one sample we made. What about the repeatability? What theory we can do it? Okay, so we looked for the theory, we follow a couple of paper. It's quite old paper in 1967. Ascot has a paper in Physical Review where he has shown in terms of if you have a correlated electron scattering, then he calculates structure factor in that thing. So we try to use those theory and try to have our own model and estimate the equation which can predict the frequency gap in short range order system, and which depend on n effective, which is an effective index of your system, and d is the diameter of the scatterer, and y0 is a factor which you get from a structure factor. So we calculate structure factor for our sample, and you can see that as you increase the diameter of scatter, the structure factor have a long frequency shift. And you can see that if you put a y0 here and measure for different sample, this new frequency gap for short range order is actually scalable, and the symbols are experiment and the lines are the theory. So we could actually repeat for different sample, and we could explain that we could predict this theoretically. Yes, you give me a sample of this diameter, I can predict where does the frequency gap comes. And then we went on to do a lot of scattering estimations. Probably I don't go detail. And we got a parameter called a negative anisotropy scattering called G value, and which is a condition which people look for the localization of light. Basically, you reduce your transport mean free path at the where you get a peak in structure factor. Unfortunately, we fight a lot in physical review letters for a year, and one referee is not at all agreeing to have in physical review letters, so they send it to PRA. And the reason is the referee saying that I had a lot of even fight with the editors that it does not have a general interest. It's very specific to optical domain. Okay, so probably the referee is confused with their own interest. Okay? So that's why. But it was a very nice work, and those who want to know the full calculation, we have a very long supplementary with this paper. It will tell you elaborate mathematics on how to calculate structure factor, the transport mean free path, and how to apply the diffusion theory to light propagations. So it will be a very nice thing for students to understand if you want to know the light diffusion disordered system. Okay, probably in 5 minutes, how much time more I have?
You have got.
Hello.
You have got more than 10 minutes.
Okay, so thanks. Okay, I think okay. So I make really a quantum gem. Okay, because as I said in the initially that I want to give an idea about different 2-3 activities happening in our lab. So I will now move into what is called a little bit of quantum photonics side. Okay, but using the same thing which you learned in the last few slides. Okay, so again, this is we are very new to this field. We just started, probably the first in the country also. Okay, we started in around 2016 with a student. I got interested in quantum photonics and especially the quantum emitters. Okay, and I'll tell you why we got motivated to this and what was it will be obvious to you in a few slides. Okay, so why you need a solid state quantum emitters? The primary thing of solid state quantum emitter is it can give single photons on demand. Okay, so you need a single photon for communications, quantum communications, and it has a long spin coherence time. You can manipulate spin of the system using optical methods, and you can read out optical methods. And the most important why this for photonics people is interesting, because this can be integrated to a photonic structures. So you see very nice pictures from different groups. So there are some 1D photonic structures, something like a laminated structure. There is a quantum emitter here. It's from University of Paris. And there's a group in University of Stuttgart where you have a pillar. You can see nice periodic structures. There is some quantum emitter here. So another photonic structure. This is another from Harvard University. Again, they have a nano pillar structure, a periodic photonic system, and then you have some quantum emitter. And this is another quantum emitter from Dick group at MIT, where they have a 2D material clubbed to some photonic structure. You can see why need to couple the quantum emitters to photonics, and that's why it got motivated me to get into the field, because we understood quite a learned about photonic structures. So can we use this into quantum side? So when you talk about quantum emitters, there are many quantum emitters available. Basically, these are defects in materials. It can be a defects in diamond, silicon carbide, even a nicely grown molecular beam epitaxy grown quantum dot is also a good candidate for single photon emissions. Okay, but quantum dots have got its own lot of disadvantage. That's why people are not much interested into that. People look for systems like defects in diamond, silicon carbide, or even 2D materials. And the most remarkable property of this system is it can use single photon at room temperature. Okay, usual experiments of involving single photon generation using from materials, it happens at very low temperature. And as I said, you can manipulate spin, you can sense magnetic field. So there are a lot of applications in magnetometry and MRIs, nano MRIs. One company in Germany is building a nano MRI, the Envision. The N stand for nitrogen vacancy centers in diamond, which I'm going to come in the next slide. Okay. So one of the defect centers that we use in our lab or our group is a nitrogen vacancy centers. Okay. So if you take a diamond crystal, we have a name similar to FCC crystals, you have a vacancy of a carbon atom, and next to that vacancy, there is a nitrogen atom. This nitrogen atom can happen either naturally, or one can artificially create it using ion implantations. And this pair is what is called a nitrogen vacancy pair. So if you have a diamond, which is a transparent material in the visible, because its a band gap is 5 electron volt, but diamond look colored, and the color in diamonds comes because of these kind of defects. And the pale yellow diamonds, if you see a diamond which has a pale yellow color, that is most probably is due to the nitrogen vacancies. And nitrogen is not the only vacancy. You can have many vacancies. You can have chromium, silicon, even tin vacancy. There are many hundreds of vacancies. Depending upon the these kind of defect state, their emission property change from 450 to 800 nanometer. And this is a spectra which I took from, I think, this Nature Communication paper. So you can see that depending upon the germanium vacancy, the emission is 600. If the nitrogen vacancy, it is around 700. Silicon is around 750. And there's another vacancy of nitrogen, nickel vacancy, which is around at 900 nanometer. So we got interested in these diamonds, defects in diamond, and trying to see whether we can generate single photons, and if one can generate single photon, can it couple to the photonic structures? So again, with more technical, so if you have a nitrogen vacancy centers, these samples can either come in nano scales, like a nano diamonds, like a particles of 150 nanometer in diameter. And you can also grow it like a thin film, like a CVD grown diamonds. You can grow the diamond in laboratory and create these defects in it. And if you measure the PL spectra or the spontaneous emission as a function of wavelength, you can see it is a very uninteresting broad wavelength, broad emissions. Okay, but what the community want, what we look for, is to have a spectra just like this. This is a cartoon picture which I made. And why do you need this spectra just like this? If you look at the ground state and excited state of a nitrogen vacancy center, we have a electronic ground state and excited. There are many vibronic levels. And if we excite this with a laser, you have a transition from 0 level to 0 level, that is 0-0 transition, without involving any vibrational quantum number or without any phonon induced transition. So this red transition, which is 0-0 line, is a pure electronic transitions, and there's no dephasing induced by the phonons. And this corresponds to the 637 nanometer in this. It's very feeble. And if you can avoid all these vibration induced, all these phonon induced transitions, and clean up the system, and you have only this one single spectra which emitted the zero phonon line, or which is a pure electronic transitions, and that's a good stuff to start with in this system. So whole effort of the quantum photonics using NV centers is primarily focused on isolating the zero phonon line and suppressing all those things. Okay, so the other application of NV center, as I said, the magnetometry, or if you have these NV centers as a ground state triplet and excited triplet, you excite it, you have a transition from up to the down level, then you have a transition slightly delayed transition. You start with an equal population in this level. At one optical cycle, you reach a level where ms equal to 0 has a more populations, and this is called optically induced transition in the system. And if you apply microwave, because this frequency is around 2.67 gigahertz, you can manipulate NVs between these two levels. And if they go from this ms equal to 0 to the ms equal to plus or minus 1, you can read out that optically as a decrease in fluorescence intensity. And this is the way you can manipulate the spin state of the system using optically and read out optically. And if you apply magnetic field, you can use Siemens splitting to split the levels. And instead of one dip, you get a two dip, because there's a transition to two levels, which is now splitted by the magnetic field. And this is the essence of magnetic field magnetometry using NV center. And you can have commercial NV center magnetometer you can buy to your lab, and you keep a sample, you can map the magnetic field and magnetic imaging. And this is one of the, this is where people talk about quantum sensing. Okay, basically they mean is very ultra low field sensing using NV center, because this defect state respond to the magnetic field, and you can read out using optical techniques. So as I said in the previous slide, that what we need is to have isolate the zero phonon line, the pure electronic transitions, and suppress all the unwanted phonon sidebands. And you seen in photonic crystal, when I talked the initial slides, we are trying to suppress the emissions. And there are different proposals recently in literature using different kind of photonic structures to suppress this phonon sideband and only get what you want, which is a zero phonon line. So we also did some experiment in this direction. So you can see that. So when you club the NV centers, basically there are many NV centers here. Club with our photonic crystal structures, you can see that the emission is suppressed in the middle in the graph here. So the black one is a reference. Again, the blue and red shows the suppression emission intensity. And if I take intensity ratio, you can see that there's a huge intensity suppression around 650 and 700 nanometer. And not only I can suppress the phonon sideband, I can, if I do very smartly, I can enhance the zero phonon line at using the band edge effect of these systems. So this is one way to control the NV center emissions. You can change the geometry, you can measure from the front side. Not only suppressing, if you want to enhance the emission from NV centers, you can do that. And this is good in cosmetic industry and bioimaging because you want more reflection, more light from diamonds. And this was quite interesting result in the sense it was published in Optic Letters and it was an editorial choice. And there was an article came in Physics World, how to make nano diamond shines brighter using these photonic structures. Okay, so our knowledge on photonic crystal we just use on NV centers to do what NV community wanted to do. Okay, and it was much simpler, so it was a good takers for it. Again, we did the lifetime measurements similar to the photonic crystal. We see whether the lifetime of NV centers can be changed. Yes, it's indeed possible that using photonic crystal, similar to the dyes we discussed, I can have enhanced lifetime. That means there's a gap effect. And we can change the geometry and we can do you can see the lifetime is now reduced because the photonic crystal acts like a reflector. So it is enhancing the emission now. So these studies has a lot of consequence in fundamental process of NV centers like charge state conversions and other things. So those probably if some of you are interested, you can look at these papers. So maybe I'll talk about in very detail in some other time. So we can control the quantum emitter properties using photonic crystals. So maybe before I end, all the NV center research, we are talking about ensemble of NV centers. So what ideally we want a single NV center, a single vacancy of nitrogen atom adjacent to a vacancy carbon atom. And once you have that system, probably that is a good candidate to give a single photon emission. But how do you know that I have a single photon emissions? The way to do, there's an intensity correlation experiment. Suppose I have a diamond here. I have a diamond here which emit a single photon. It comes to a 50-50 beam splitter. Either it can go to D1 detector or D2 detector. It cannot go to both detectors simultaneously. And this is called the coincidence measurements. And we look for this coincidence in intensity, but at zero delay. So you expect this zero delay, you should not get a peak. That means only one detector got a single photon. But unfortunately, we did not get a single photon. So our efforts are in these directions and probably we'll have a soon that result. This is quite old slide. I think we have almost reached that level to detect it and doing a confocal scan of the samples so that you identify all these individual defect centers. So this is an ongoing effort. We got 50% of our lab activities into these directions. So search for the single photon, then entangle the single photon with the spins in the system. Okay, so just to conclude, I think I've eaten up a lot of time. So I hope you are able to convey you some interesting optical experiments that if you can cleverly do the experiments, even self-assembled systems can be a useful stuff to study all these nice fundamental emission properties. And I also discussed with you how when you induce the disorder in the system, you can also get a frequency like a short range ordered system, and that will give a frequency gaps. Then some of our understanding or some of our initial results on how we can control the NV center. In case if you don't understand it in my talk, you please read these papers. These are selected papers from our group published in the lab. And so important results are also given here. So before I stop, I speak a lot, give talks on an average 2 talks per month, but it's my student who works in the lab, and because of that I could present all these things to you. And these are my current students, and 2 students is coming this month probably, one JRF and one postdoc. And 3 students are graduated. I took some result from their thesis to present. The Priya is the first student doing a postdoc at France. Sachin is doing at City University New York. Sudhir is doing at postdoc at Chanda University. And I was immensely helped from our master students and many summer interns and my collaborators. And being an experimentalist, the only thing I asked to everybody is money, money, money. So we have a huge funding, and we are fortunate and lucky that nobody has denied any grants to us. We are also part of the National Initiative on Quantum Science of the Government of India, where they're funding an activity on NV Center. And this year, Swarna Jayanti Fellowships, we are having an activity on doing all these experiments at low temperature at the 4 Kelvin and using instead of photonic crystal, photonic cavities, and trying to make a single photon emit faster than its natural lifetime. So that's what the project is all about. And we got around huge funding of the order of 5 to 6 crores to build up these facilities at Ropar. So if any of you are interested, PhD or postdoctoral positions, please contact me. And we have 3 fully funded PhD positions in the next summer. So with this, I thank you for your time and thank you for this invitation again. And if you have any questions, I would like to answer.
Thank you very much, Dr. Rajesh, for this very interesting talk, sharing a lot of exciting results. And we have a few questions already here. So I'll just read this out for you. So the first question, I think it's regarding the emission experiments that you were discussing. The question is, isn't excitation depend on density of states? If density of states is very less, then how does the excitation happen?
Okay, nice question. So excitation, the question is correct and relevant, but the excitation is not at the band gap frequency. If my gap is at 600 nanometer, the excitation is at 530 nanometer. So for 532 nanometer, the sample look like a homogeneous medium. It will transmit the light. So that is you have to very careful. So you excite at a far tuned wavelength, let's say 530 nanometer in our experiment, and looking at the emissions which happens at 600 nanometer. Okay, so 530 nanometer will propagate to the system and it is a transmission band. So it's not in the frequency gap. So there'll be no problem of density states.
Okay. The next question is more regarding the colloidal self-assembly. So it's about the experimental setup. So how do you, the question is, do you have a chamber in which the self-assembly happen where you can control the humidity and temperature?
Okay, with my experience, none of the reports in literature works because people do not reveal their secrets. And so we have this monodispersed colloid. One of the reason is you should have a highly monodispersed colloids that you have to get from industry. If you try to make it, it will be monodispersed, polydispersed. So we have a temperature controlled oven. And these samples are, you optimize the concentration volume. So you have a small vial kind of things. So you take this colloidal suspension, you insert a kind of a glass substrate into that at an angle. And this is kept at a vertical, the substrate is vertical and the entire thing is closed and in a controlled temperature. So samples I have shown is made at 45 degree, I think, to have the sedimentation to happen, the suspension evaporate. Okay, and the sample growth take a week, 5 to 7 days. Okay, if somebody during that time, your friend came to try to help you, increase the stability or assembling, try to shake the oven, the entire thing collapsed. So you have to be a very isolated place and we have a very strong bench and the oven is also very heavy. So once you put it, you can only open after 7 days. So you know whether you are luck or not after 7 days. Yes, it's very difficult. It is not a difficult. It is, you need to have your recipe. Okay, once you have your recipe, it will work. Okay, and also with our experience, we also with our experience, what we found that the growth of a 300 nanometer particle is quite different from a 1 micrometer particle. So you have to really another optimization for that. Okay, but it is not hard. It's not that you don't need a very high-fi techniques or anything. You can do it in your lab.
Okay, then we have another question. Is it possible to control the magnetic dipole emissions using photonic crystals practically?
Actually, I do not know about that. I don't know the answer straight to that. So what I seen in literature is that people try to do this magnetic dipole control or electric dipole control or get both happens at the same wavelength, what people call is a Kircher condition meta surfaces. Um, there, I do not know in photonic crystal because we never worked on any magnetic photonic crystals. Okay, so I do not know, but I know that in the case of meta surfaces like a 300 nanometer pillar kind of things. Okay, so where people can try to get this magnetic dipole control. So if somebody is interested, please look at the paper by Yuri Kivischer from Australia. So they do every month they have papers on how to control magnetic dipole and electric dipole and get at both these dipole at the same frequency and what they call Kircher conditions. So I do not know that man's. So please look at that paper.
Okay, thank you. And I think have one more question here that is about what happens to the transmission properties when dispersive materials are used in the structure?
Okay, if the dispersion is mean is absorption, and then everything will collapse. Okay, the first and foremost idea that in experiments or in theory, all these nanophotonics, not in photonics, in general, there should not be no absorption. Okay, yes, there are very different group try to enhance absorption in the systems. If you have an absorbing material in the system, then the things get collapsed because then light absorb. You can't do any purpose. Okay. So we try to avoid any dispersion. And if you mean the frequency dependence of dielectric constants, that will change because then the refractive index will change. But we try to work in a frequency range, at least there is no much change in refractive index. So for example, you see the polystyrene. If you do experiment at 600 nanometer, 800, there is not much change in refractive index. But if you go to 200, 300 nanometer, the dispersion curve actually goes up. So then you need to worry about those functions.
Okay, so one more question about the experimental setup that you showed for the micro imaging. So you used continuum source, right? In white light continuum.
Yeah, super continuum.
Yeah, super continuum. So why did you go for a super continuum rather than a normal white light source?
It is just a comfort only. In principle, you can do with your halogen lamp also. But then the question is the collimation and the focusing and all those things. In the olden days, people do with halogen lamp. Maybe 10 years back, replace with that.
Okay.
So it's just a convenience only.
The concern this is about see the supercontinuum is produced by, I mean, what is the kind of the time pulse width that you have because supercontinuum if it is generated from a femtosecond
this is picosecond,
or if it is a okay. So since photonic crystals are how do they act when you have a picosecond signal going into the crystal? Will it affect somehow in terms of dispersion, or is it okay to use?
No. As far as our expense are concerned, we never have any issues like that because we are not looking at any time domain measurement. We just this fast picosecond pulses, the very repetition rate, and you just measure the reflected light only. And it's a normalized with this reference, which is done with the same system. So I do not know where, because we did not do any pulse experiments, any temporal experiment, how the pulse propagate to this, how much it broadened, those kind of time of flight kind of experiments. So we just measure reflection. So we do not face any problem in this experiment, and it's also reproduced with theory. So, and the reason why I use picosecond this pulse laser because just convenience. You have a nice collimated beam with it's easy to manage in experiments rather than a halogen lamp. You can do with halogen lamp, absolutely no issue. Okay. Even people do not only for supercontinuum source, people do with tunable laser source also, measurement or reflection and transmission.
Okay, thank you, Dr. Rajesh, for clearing all these questions as well, and it was a wonderful session for us. Thank you once again for this talk. And I also would like to thank you from a part of all the faculty members and students of ISP. Thank you for joining us today.
Okay, thank you.
Thank you, sir. Thank you very much for being part.